Hello and welcome to the world of chemistry. Today we want to talk about two specific things, and that is Lewis structures and the shape of molecules as determined by valence shell electron pair repulsion. An important thing about this video is that I'll be able to show you things in 3 dimensions that we have to look at the textbook in 2 dimensions. And there's a very special way to look about things in 3 dimensions in chemistry, because the shape of the molecule in the end determines what fits an enzyme molecule, the kinds of properties that a particular compound has. So the first thing is the Lewis structure. And the Lewis structure is just a process that you have to be able to do. And I thought we would start by writing the Lewis structure of a compound, and we'll choose ammonia. So the formula for ammonia is NH3. From this formula we get all of the total valence electrons. Each atom brings valence electrons. And so we look at the ammonia and we see nitrogen, and we look at the periodic chart and we find nitrogen very easily over here. It's in group 5A, which means it has 5 valence electrons. So it brings 5 electrons in it. And then each hydrogen brings, it's in group 1A, so each brings 1 valence electrons. So from hydrogen, you have 3 of those. 3 times 1 electron equal 3. So 5 plus 3 means we have 8 valence electrons. So that's the first step, is get the total valence electrons. The second step is to connect the atoms. And if you connect the atoms, you'll choose one as central and you'll connect it to the peripheral ones. And so the connecting atom is usually the one that lies further to the left, other than hydrogen. So nitrogen is the central atom, and we connect it up to 3 hydrogens. Oops. And what this line represents is a bond pair. So it consists of 2 electrons. I like to use the lines for bond pairs, but you must understand that's really 2 dots or 2 electrons in there. So in doing that, I have used 2, 4, 6 electrons. So let's do the math here. 8 total available minus 6 for the bonding leaves me yet with 2 electrons to distribute, according to the correct theory of Octet Rule. Now the Octet Rule says that every atom needs to have 8 electrons around it. But there are some exceptions, and one exception is hydrogen. It can only accommodate 2, and boron usually accommodates 6. But all the rest of the atoms accommodate 8, and so we have what is known as the Octet Rule. So we start always with the peripheral atoms and say, are they satisfied? Well, here's hydrogen, and it has 2 electrons. This bond pair counts for both hydrogen and nitrogen. So each hydrogen has 2 electrons, so it's done. Okay? We still have the same 2 electrons that we haven't done anything with. So now we look at the central atom. We put them on the central atom, and now we've taken care of those 2 electrons. We now have our Lewis structure showing with the total of 8 electrons. And then we check the central atom, and it has 2, 4, 6, 8. The Octet Rule is fulfilled, and this is the Lewis structure for ammonia. And to characterize it, we say that it has 4 regions of density. 1, 2, 3, 4. 3 bond pairs plus 1 lone pair equal 3 regions of density. So that's the important thing, I think, for getting the Lewis structures, is to get the central atom, figure out what kinds of bonds, are they single bonds, double bonds, lone pairs, and then come up with the number of regions of density, because that'll determine the shape ultimately. My second example is going to be a molecule. Let's take this molecule. And that is a dichloromethane. ANE, or methylene chloride. You don't have to know the name of this compound, but it's a covalent compound. And so we quickly get the total valence electrons. We know each hydrogen brings 1, so 2 times 1 for the hydrogen equal to each carbon in group 4A brings 4, and each chlorine in group 7A of the periodic chart brings 7, but we have 2 of those, 14, 8, 10, 20 electrons to work with. So we have 20 valence electrons to work with. That's the first step, getting the total valence electrons. Now the next thing is to connect them up. The connectivity is we'll put carbon as the center line. It's the one furthest to the left in the periodic chart other than hydrogen. And we're going to connect to a chlorine here, a chlorine here, a hydrogen here, and a hydrogen there. This then is the connectivity. So now, how many electrons did we use to connect it? Well, we have 2, 4, 6, 8. So we're going to take -8, and that's going to leave us with 12 electrons left. So now we have this 12 electrons that we have to put onto this Lewis structure. And the way we're going to do that is we're going to start with the peripheral atoms and complete their octets. So we look at this peripheral atom, and hydrogen with its 2 is already completed. This one is already completed. But chlorine, you see, has only 2 electrons and it needs 8. So we'll just put these 8 on here. We'll put 6 more, 6 plus 2, 8. So we've used 6 plus 6, we use the 12 electrons. We don't have any more left. We cannot add any more electrons. And the normal thing you would do is you would then look at the central atom and check its octet, and it's complete, 2, 4, 6, 8. So this then is a completed Lewis structure for methylene chloride or dichloromethane. Around the central atom, there are 4 regions of density. Okay? And they're all bonded electrons. Let's do one more in which we might have to do a kind of a different decisions. We'll do SO2, sulfur dioxide. Sulfur dioxide, both oxygen and sulfur in group 6A. So each one brings 1, 2, 3 times 6. We got 18 electrons to deal with. So we connect them up. S, O, O. To connect them up, we use 2, 4 electrons. -4 means 14 electrons left. Okay? Go to the peripheral atoms and complete their octets. You can see they all need 6 electrons to complete the octet. And that uses 12 electrons. And I still have 2 electrons left. The 2 electrons then have to go to the central atom. And I've used up all of my electrons. Now the last checking point is how many is the octet of the central atom completed? Well, you look at it, you have 2, 4, 6. It is not. It is not completed. We need to have 8 electrons. And so now it comes the choice in which you can move a lone pair off of one of these atoms and put it in as a bond. That way it counts for both of them. And so we redo that, and notice this would have resonance because I could have chosen this atom or that atom. But that's not going to be terribly important for us now. The final structure that we should come up with, the Lewis structure, is going to be like this. Okay, so now we make a decision about how many regions of density do we have around the central atom. Well, we see we have one region of density, so we have one single bond. We have this region of density, and notice even though it's a double bond, it's one region of density. So we have one double bond. And we have this, which is one lone pair. So we have 3 regions of density. And that's just, that's my demonstration, I think, of writing Lewis structures. And what we're going to do with these Lewis structures is the next part of this presentation. And it's about how to use valence shell electron pair repulsion theory.